And today we'll continue with fluid deformation. So for a fluid, we can define angular deformation. As we have seen last time, any particle in motion, if it's undergoing rotation, can undergo also angular deformation. And we can compute the rate of angular deformation by knowing the velocity field. So knowing u, v, and w will allow us to determine the rate of angular deformation. For example, if we want to know the rate of deformation in xy plane, we just have to assess the component del v by del x plus del u by del y. And if we want to find the rate of deformation in yz plane, then we should use del w by del y plus del v by del z. And finally, to get the rate of angular deformation in zx plane, we should compute del w by del x plus del u by del z. Now, in particular, okay, if we have one-dimensional laminar Newtonian flow, we know that the shear stress can be related to the deformation. If you have one dimensional flow, okay, this means that you have flow in one direction, for example, in xu. Okay, if we consider, for example, the flow in a let's say in a between flat plates, okay, we can say that in this case u is only function of y. Okay, so if u is only function of y, this means that del u by del y is equal to the derivative of u with respect to y, and all other terms will cancel out because no v. So del v by del x is 0, no w also, and u is only function of y, so del u by del z is 0. This means that if you have 1D flow where u is only function of y, you will only have a rate of angular deformation in xy plane, and this rate will be equal to du by dy. Okay, and by definition, for a Newtonian fluid, the shear stress, we have computed this before, is mu times the rate of deformation, and in this case the rate of deformation is du by d. Okay, let us do an example to practice on a little bit on angular deformation and rotation. If we consider the following example, a viscometric flow in the narrow gap between large parallel plates is shown. The velocity field in the narrow gap is given by v equals to u times y over h, where u is 4 millimeters per second and h is 4 millimeters. At t equals 0, line segments AC and BD are marked in the fluid to form a cross as shown. Evaluate the positions of the marked points at t equals 1.5 seconds and sketch for compounds. Calculate the rate of angular deformation and the rate of rotation of a fluid particle in this velocity field and comment on your results. So this is an example of 1D flow. Okay, you have flow along one direction, along x, and the profile of velocity is only varying with y, and the equation is given here. They gave us the equation of the flow field, of the velocity of the flow field, v equal u times y over h. So it is a linear profile. It starts by 0 due to the non-slip condition because the bottom plate is fixed, and since the upper plate is moving at velocity u, this will give the fluid at the upper level a velocity u. So you have a linear variation of velocity from 0 to big U due to viscous effects. Okay. Now, since no velocity along y, so if it means if I have a particle here, this particle, if I follow it, if I track it, it will move in the horizontal direction. It cannot move in the vertical one since v is 0. Okay. So if you want to know the displacement of a particle, all you have to do is to compute its velocity, and this velocity is not changing with x, so v is constant. Then for a certain time, you can say that the displacement delta x is the velocity at this location times delta t. Now, how to get the velocity at a certain location? Just we have to replace to know y of the particle. So we have to do u times y over h. For example, here in this problem, they are giving us a cross of 4 points A, B, C, D. and we are interested in the motion of these points. Okay, so if I take particle A and particle C, both have same y is equal to 2. So for both of these particles, y equals to 2, and this means that the velocity of these points, A and C, is equal to big U times y, which is 2, over h, which is 4. So for these two, we have a velocity of 2 millimeters per second. Okay, and to know their displacement in 1.5 seconds, all we have to do is to say that A and C will be displaced horizontally and will move a distance delta x of A and C is equal to 2 times 1.5. Of course, you have 2 is in millimeter per second, and 1.5 is in second. So what will happen is that second will cancel out and you will get your result in millimeter. So the displacement of A and C will be 3 millimeters. And both will move the same distance because they are at the same level, at the same horizontal level, so they have same velocity. On the other hand, if you consider points B and D, they have different y. So each will move a different distance, okay? For point B, what is y? It's 3. So for point B, if I calculate velocity of point B, I just have to do U times y of B over h. And y of B is equal to 3. So it will give me then velocity of B is 3 millimeters per second. So B will move faster than A and C because it's at a higher height. Okay, and then delta x of B is calculated as 3 times 1.5. So B will move 4.5 millimeters. While point D has y equal to 1. So the velocity of this point will be 1 millimeter per second. Okay, and then it's moving 1 times 1.5, it will move 1.5 millimeters. So now, if I want to plot the motion of these points, I get the following sketch. As you can see, AC will move the same distance, while B will move the largest distance between the points, and D will move the smallest distance because it is characterized by the smallest velocity, since it's closer to the bottom plate. So now, as you can see, you have angular deformation for the vertical line, while the horizontal line will remain in its same direction in the horizontal line, because along this line you have no change in velocity. While along BD you have change in velocity, this will lead to a certain angular deformation. And if you want to compute the rate of angular deformation, all you have to do is to go back to the formulas. Okay, if we go back together to formulas, here u is only function of y. Okay, we have seen together today that angular deformation in xy plane is equal to del u by del y plus del v by del x. You don't have del v by del x, so the only term is del u by del y. And u by definition is u times y over h. So if you derive u with respect to y, you will get u over h. So the rate of angular deformation is u over h, and the unit of this rate is a second minus 1. Okay, and if you replace into the formulas of angular deformation in xz and yz, you will get 0. Why? Because as I told you before, if u is only function of y and v and w are 0, all terms will cancel out. We will only have a deformation in xy plane equals to del u by del y. Now, if you want to get the rate of rotation, the angular rotation, you should get omega. Okay. Now, to remind you of the formula of omega, we will go back to the previous slides. We introduced this concept last time. Here you have the formula of omega in cylindrical in Cartesian coordinates. So this is the formula of omega. Omega is half of del W by del Y minus del V by del Z along I. But for this flow, no W, no V, so these terms will cancel out. Along J, it's del U by del Z minus del W by del X times 1/2. U is only function of Y, so del U by del Z is 0. And W is 0, so this term will drop. And the final term, you have del V by del X, no V, so this is 0. So you'll end up only with W in this case is only along Z and is equal to half to minus half del U by del Y. Okay, so now you just have to replace del U by del Y for this problem by U over H. Okay, and you will get your angular velocity. And why here it's negative? You can expect this because look how BD is turning. BD is turning clockwise. So omega Z is negative because this is I, this is J, and K is positive towards U, perpendicular to the screen. So the positive WZ is counterclockwise, while negative WZ represents clockwise rotation. And here the rotation of BD is clockwise, so we expect that omega Z is negative. Okay. Any question on this? Now we will introduce momentum conservation in differential form. So we will follow here, if you want, as we did in the previous chapter. We applied continuity equations and we applied linear momentum relation for a certain control volume. We are doing now the same procedure, but we are considering a micro element, a very small volume. Okay, so the formula to apply is exactly the same, but now we are taking an infinitesimal control volume. This means that we have to apply the Reynolds transport theorem on V to get the linear momentum equation. And no need to do any integral here because you have just one small element. Okay, so if you apply the linear momentum on this small volume, you get sum of external forces acting on the system is equal to sum of linear momentum fluxes at outlets, so sum of m dot v. And here we didn't perform any integration because, as I told you, you are taking a very small element, so along a certain phase the velocity is not changing, so you can consider that v is the same over the phase. So for outlets you have sum of m dot v at outlet, and as usual for inlet you have the negative sign, so minus sum at inlet m dot v. Now this represents the storage term of linear momentum, so it's del by del t of rho dv times velocity vector. Now dv here, the volume here is dx dy dz, so we can replace dv by dx dy dz. Okay, now we will try to study together the different terms. So what should be included in sum of forces? What should be included in sum of linear momentum fluxes at outlets and inlets? And to come up with a general relation for momentum equations. Okay, so let us start by finding the different terms. Okay, first, when we talk about fluxes, okay, fluxes at inlets and outlets, we should consider for each phase fluxes crossing it. So for example here, if you look at this figure, okay, you have, for example, here you have, this is an inlet and this is an outlet. So for this inlet, the flux can be written as, you know that m dot is rho VA, rho times velocity times area. Okay, so for example, if you consider the following phase, the following phase is characterized by an area equal to, you have, this is along z. So this is dz, and this is along y. So this is dy. So the elementary area for this face is dy times dz. Okay, and you have that the velocity which will contribute to m dot is the velocity component perpendicular to the face. The velocity component that is perpendicular to face yz is u. Okay, this is why you will multiply rho by u by dy dz. This will give you m dot at the inlet at this face. Okay, and of course, since you want to find the momentum, the linear momentum, we'll multiply this m dot by the velocity vector at this location. Okay, now for the outlet flux, we can use here the Taylor expansion method, okay, with the truncation error, because we are just considering the first of order of first derivative. You know that in Taylor expansion you have several terms, and you add terms proportional to the first derivative plus terms proportional to the second derivative, etc. But since you are considering a very small element, you can consider that all other terms will be negligible compared to the first two terms. So we say in this case that the error is small, and we can approximate from Taylor expansion. If I have here a certain function at x, and I want to compute the value of the function at x plus dx, okay, I can just say that from Taylor expansion, f of x plus dx is equal to f of x plus del f by del x times dx. Okay, and we will apply this now for which function? For function rho uv. So if we have function rho uv at this face, which is at a certain section x, and we want to determine at x plus dx what will be the value of rho uv, you can simply say that at this face you will have rho uv plus del rho uv by del x dx times dy dz. This means that we account that rho uv might vary from this face to this one. Okay, so we do the same procedure for all other inlets and outlets. So the only difference, for example, here is the direction of the flow. So here, when you calculate m dot, you should consider v component of velocity, which is along y. So you do now rho v times velocity vector times the face here area is dx dz. And at the outlet, you do the Taylor expansion to compute the value of rho vv at this level, which is rho vv plus del by del y of rho vv times dy. Okay, and the same in the final direction here. You will consider w as the velocity component crossing the face. So this will give you the different expressions of linear momentum fluxes at inlets and linear momentum fluxes at outlets. Now, concerning this term, okay, since dx dy dz is a fixed volume, you can take it outside of the integral, and then this term will give us dx dy dz times del by del t of rho. And this is a non-steady term. If you have steady state case, then this term will cancel out. Okay. Now, let us move to sum of forces term. So now we should compute what is sum of forces. Before going to sum of forces, let us replace summation of m dot outlet v here and summation of m dot inlet v for these different expressions, and come up with simplification for the second term of our equation. So if you replace the different fluxes terms, you will end up with several simplifications, because as you can see, for example, here you have plus rho uv dy dz. Here you have minus rho uv dy dz. So this term will cancel out. Here plus rho vv dx dz minus rho vv dx dz also will cancel out, and this one will cancel out. Now, if you pay attention that all your terms, okay, contain dx, dy, dz, and this term at the end will be simplified. So now, if you just compute some m dot v out minus some m dot v in, this is the term you get. So you just have three terms: del rho uv by del x times dv, plus del rho vv by del y times dv, plus del rho wv by del z times dv. Now, let us compute the remaining terms. We still have to compute sum of forces terms. When we consider sum of forces, remember that these are external forces, and in general, you can have different types of forces. You can have pressure forces, you can have shear forces, you can have body forces. So here we'll include all possible external forces. To do so, okay, in a most general case, for a certain phase, we can consider three orthogonal stresses in the different directions, x, y, and z, okay? And how we put the subscripts, for example, for a certain stress, the first subscript, so this stress is sigma. First, you put the first subscript correspond to the direction perpendicular to the face. So here you are working on this face. This face has a normal vector along y. So because the normal vector to this face is along y, the first subscript for sigma here is y. And the second subscript represents the direction of the stress. So here, for example, the stress is along x. So this is sigma y x. Okay. Now this one, for example, we are in the same phase. So the first subscript is y, while the second subscript represents the direction of the stress, which is z. So this is sigma yz. Now both sigma yx and sigma yz represent shear stresses, okay? While sigma yy represents pressure forces or normal forces, okay? Now, we can define for each phase three stresses. So we end up with a matrix of 9 stress values, okay? That can be normal, decomposed into 3 normal stresses and 6 shear stresses, okay? So we know that now, if you want to write the balance of forces, for example, if you consider first all 4 possible forces in x direction, okay? You have possible forces in x direction will include all sigma, which having the second subscript x, because all sigma having the second subscript as x will act along x direction. So in this figure, we represented all forces along x, okay? And as usual, we consider that if along a certain face I have sigma yx here, for example, then on the upper face, okay, I will have, by using Taylor expansion, the value of sigma will be sigma yx plus del sigma yx by del y dy. Okay, and you know that the stress unit is Newton per meter square. So to have it in unit of Newton, I should multiply by the area of the force. Okay. So now all I have to do is to sum all forces along x according to this figure and do corresponding simplification. If you look at the following figure and sum all forces along x, at the end you will have several terms that will cancel out. So sigma xx minus sigma xx dy dz, sigma zx minus sigma zx dx dy, etc. So these terms will cancel out. And you will end up, and also don't forget body forces. Body forces is due here to gravitational force. So here x, y, z are coordinates of any orientation. يعني يمكن y is not the vertical here. So you can have x, y, z in any orientation. This is why, since g is always vertical, we can decompose it. So for example, maybe if you have here x, y, z inclined, g can be with respect to this frame like this. But g is always in the vertical direction. So this means here that the vertical direction is somewhere here. It's not along y or x or z. So you can decompose g vector into components gx, gy, gz. Now, in case y is the vertical direction, then you will only have gy equals to minus 9.81 or minus g, depending, g depends on the altitude. So if you are close to the earth, you can take g 9.81. Okay, so here we consider any possible orientation for x, y, and z. So body forces will be decomposed into three components: rho gx dv along the x, rho gy dv along y, and rho gz dv along z. Okay, so now we have calculated all terms of our relations. All we have to do now is to replace back into the equations. Okay, now before replacing, as we did exactly for x, we'll do for y direction to get sum of y, and for z direction to get sum of f. And now if you replace back in your relations, you will get the expressions of sum of x, sum of y, and sum of fz. Okay, so these are the final relations for sum of x, sum of y, and sum of z. So now all we have to do is to replace into the equation. Okay, so already we computed the left hand side of the equation, which is sum of forces, and the right hand side, which is sum of m dot v at outlet minus sum of m dot v at inlet plus del by del t of rho dv times v. Now, as you can see, all terms include dx, dy, dz. This is a common term for all equations. So because it's common, when I plug into the equation, I can simplify this term. So before proceeding, we'll divide the two sides by dx, dy, dz to simplify the equation. And we will end up with the following relations. Okay, so along x, this is called the linear momentum equation along x. This is the linear momentum equation along y. And this is in differential form, of course. And this is the linear momentum equation along z. So in this stage, the relations are still very complex because you still need to relate stresses to your velocity field. Okay, and this require additional sciences to go over. So for example, to be able to relate stresses to strain rate, we need information from rheology. Okay, now we will take together a particular example, which is the case of Newtonian fluid. If you remember at the beginning of this course, we defined several types of fluids: Newtonian, non-Newtonian fluids, etc. Okay, and we said that the property of Newtonian fluids is that mu is constant. So in particular, if I have mu constant, I can write a relation between the stresses, the shear stresses, and the rate of deformation of the fluid. Okay, so here I can relate the stress strain rate depending on the type of fluid. In particular, for Newtonian fluids, the relation is linear with a proportionality constant, which is the viscosity. Okay, so in case you have in this course, we'll just consider the case of Newtonian fluids. So you will replace sigma xx by minus p, which is the pressure term, plus 2 mu del u by del x. You will replace sigma yy by minus P plus 2 mu del V by del Y, sigma ZZ by minus P plus 2 mu del W by del Z. Now, in case of a Newtonian fluid, you have that sigma YX equals to sigma XY equals to mu times del U by del Y plus del V by del X. And sigma ZX is equal to sigma XZ equals to mu del W by del X plus del U by del Z. And also sigma ZY is equal to sigma YZ equals to mu del W by del Y plus del V by del Z. Okay. Now we will plug into the momentum conservation equations these relations between the stresses and the stress strain rate. And we will consider cases of incompressible fluids, so density is constant and viscosity is constant. And this will give us the famous Navier-Stokes equations. Okay, so Navier-Stokes equations can only be applied for these equations presented here, can only be applied for a Newtonian fluid that is incompressible. Okay, because we considered the assumption of incompressible to take rho outside of that. Because if you remember here, you have, when we wrote the equations before doing simplification, rho was inside of del. So to be able to take the rho outside of del for all terms, we should have the assumption of constant rho. If rho is variable, this will complicate the solution more. Okay, so in this course, we'll just consider solution of flows in case we have laminar Newtonian incompressible fluids. Okay. And of course, we'll take solutions for laminar flows because when you have turbulent flow, this will complicate a lot things. We should add another variable, which is turbulence, to be able to solve for fluctuation of the flow. So for Newtonian incompressible flows, we can write what is called the Navier-Stokes equations, which represent the linear momentum relations in X, Y, and Z. And now, always don't forget to combine these and the continuity, because the continuity equation will always give you a certain information to solve for your flow field. Okay, so these are Navier-Stokes relations in Cartesian coordinates, and this is the continuity equation for incompressible flow in Cartesian coordinates. Now, let us do interpretation of each of these terms. So first you have this term represents the local acceleration because it represents the variation of velocity with time at a certain point. If you remember, when we defined acceleration, we said that acceleration can be divided into two parts, local acceleration and convective acceleration. Local acceleration means if we have variation of velocity at a specific location with respect to time, while convective acceleration means that if velocity is varying with position. So here, the summation of these three terms represents the total variation of velocity with position. Okay, so u, for example, along x, u del u by del x plus v del u by del y plus w del u by del z represents the convective acceleration term. So these are the summation of these will give us the total acceleration. And as expected here, you know that sum of forces is equal to ma. We started from sum of forces equal to ma for a rigid body, and so we know that when we consider a, here's the total acceleration, sum of forces equal ma in case of rigid bodies or in case of fluids. So now here, what we did, because we simplified, we started from this relation, okay, and we simplified by saying that m is rho times dv, and we simplified our both sides by rho and dv. This is why after simplifying rho and dv from all terms, okay, we end up with a term of unit of acceleration. Okay, so originally we started from forces, so unit was Newton, but since we divided all terms by rho and dv, we end up with terms of a unit of acceleration. So this is the total acceleration that is divided into local and convective acceleration. And now from the other side, we have all, if you want, all forces terms, okay? So this is related to the gravity force per unit mass. This is related to pressure gradient force per unit mass. And this is related to viscous forces per unit mass. So as you can see, after writing the linear momentum equation, we develop the relation sum of forces equal ma for a fluid element. Okay, so this is what we end up with. We end up with sum of forces equal to ma for a very small control volume element of volume dx dy dt. Okay, so this is our final result, and these are called, as we said, Navier-Stokes relations, and we'll use them to solve for the velocity field and for the pressure field. We'll do together several examples to see how we can apply these relations for certain typical cases, particular cases, where we can obtain a direct analytical solution. Okay, now in cylindrical coordinates also, as we did previously in all parts, if you remember, we are defining all properties as deformation or acceleration or continuity or linear momentum in two systems: Cartesian coordinates and cylindrical coordinates. Okay, so this is why here also for Navier-Stokes equations, we'll define them in polar coordinates or cylindrical coordinates. In this case, we can relate always polar to Cartesian coordinates, because you have that if you have XY system, to move to polar coordinates, you just define an origin O. You consider R is a position vector, and theta is the angle with a reference line. So for example, theta angle with X. So you can switch from coordinate to coordinate system by saying that X is R cosine theta. So if I project here, I get X. X is R cosine theta, and Y is R sine theta, while Z is the same for both planes. Okay. So now, in polar coordinates, I can develop a continuity equation. We already have seen this continuity equation for incompressible flow before. So in polar coordinates, the continuity equation is of the following form: 1 over R del by del R R V R plus 1 over R del by del theta V theta plus del by del Z V Z equals to 0. So this is the continuity equation in polar coordinates. Now, also, we can define Navier-Stokes relation in cylindrical coordinates. So we have that these are the Navier-Stokes relations in cylindrical coordinates. So of course, you don't have to remember any of these. They will always be provided to you in formula sheets. All you have to do is to know how to apply them. Okay. So for example, if they tell you, for example, that you have a velocity field that is characterized by VR, that is only function of Z, for example, and you don't have other components. So in this case, you can simplify a lot of terms, because, for example, if VR is only function of Z, so del VR by del R will be 0. And del VR by del theta will also be 0. You will only have del VR by del Z. And since you only have VR, all other velocity terms will cancel out. So no V theta. So also V theta is 0 and Vz is 0. Okay. So this will lead to a lot of simplifications in your terms, because, for example, in this type of flow, if I go to these equations, first I have rho del VR by del T. If you have steady application, so for example, if I add for you that it's steady, so this term will cancel out, for example. This term will cancel out, and you have del VR by del R is 0, no V theta, no VZ, so these terms will cancel out. From this side, you have del VR by del R is 0, del VR by del theta is 0, no V theta. You only keep second derivative of VR with respect to Z because VR is function of Z. So depending on the type of problem, you can do a lot of simplifications. And you will reduce a lot these terms. And these long equations will reduce to simple equations that can be solved analytically. Okay? For example, for the second relation, if you want to take this specific case, all terms of V theta will cancel out because V theta is 0. So from this side, you'll have a lot of simplifications. And VR is only function of Z, so del VR by del theta is 0. So here, you just get, for example, in this case, that this term is equal to 0. So this will help you to get the pressure variation with respect to that. So by solving these relations, you can get expressions of pressure and expression of velocity field. Now, the third relation, if you want to simplify it in this case, you have Vz is 0. So all of these terms will cancel out. And also these terms will cancel out. So you will end up with the following relation. So this will give you how pressure is varying with Z. So from this relation, you get how pressure is varying with Z. You integrate and with respect to Z, and this one you integrated with respect to theta, and you compare both results to be able to identify the pressure relation. Okay, and once you get information about your pressure, you can plug it here, and then you can solve for your velocity field. We'll do a lot of examples to practice on this. So this is just to tell you that it's true that this equation seems very complex, but when you consider some specific cases, a lot of simplifications will take place. Okay. So also we can write this Navier-Stokes relation in the following form. So just it's a mathematical operator if you want that simplifies the relations. But I know that you prefer this, because mathematical operator at the end always have a certain symbol. So for example, you have here, this symbol is for the following term, VR del by del R plus 1 over R V theta del by del theta plus VZ times del by del Z. So if you want, you can directly use the previous form because it's already plugged in and the mathematical operator are replaced by the corresponding values. Okay. So this is about Navier-Stokes relations. Okay. Now we will start to apply these relations in different types of problems. We will consider first the case of a flow between parallel plates. Then we will consider the case of flow in circular ducts. So for example, in case of parallel plates, we'll use Cartesian coordinates, while in the case of a cylinder, we will use polar coordinates. So we will practice on different geometries to see how we can apply continuity and Navier-Stokes relations to come up with equations for the velocity field and pressure field.